Okay. Hi, everybody. So today what we are covering is on the third chapter, which is Probability and Distributions. Okay. So although this may look like a very extensive and long chapter, we'll try to break up into different parts. I'm Morris Ling, by the way. Okay. So why do we actually need to learn about probability? In later chapters, you will deal with this part of statistics, and one of the most important concepts is this thing known as p-value. The p-value simply means probability value. Okay? And that is the reason why we need to talk about your probability in the first place. Okay. So there are a few primary aspects of our probability. Not all of them are as important as what they are. But what we want to give you is a basic construct of what it needs for you to understand to a later chapters. So there are actually 8 different parts. Your basic counting concepts, permutation and combinations, what they are, and then what you have is your probability itself. Talk about mutual exclusivity and independent events. This is a very important subchapter. Okay, your conditional probability. From then on, we look at what on earth does random variable means. From random variables, we talk a little bit about binomial distribution. Then we talk about normal distribution. Okay, normal distribution is a very important chapter or subchapter because in statistics, your normal distribution is actually the fundamental aspect of all statistics. If you can understand normal distribution well, the rest of other statistics can be within understanding within your grasp. So what you need to do is how to actually construct Venn diagrams. What are probability? How to calculate probability? How to construct Venn diagrams, especially your tree diagrams, and on conditional probability as well. Okay, so we talk a little bit about binomial distribution because that is we need it for your normal distribution. How does binomial go into normal distribution? Okay, and then we need to derive your cumulative probabilities. Okay, so without further ado, let's go to it. Okay, let's look at counting principles. So counting principles talks about how many ways are there to do two different things or multiple things. Okay, you look at, because it's counting, okay, counting, you're looking at how many ways to achieve a task. Okay. So in this case, there are actually 2 basic principles. One is the addition principle. Okay. By definition, if A and B are 2 events that cannot occur at the same time, cannot occur simultaneously, that means they are disjoint. Okay. So how many ways can happen? Okay. So for example, if event A has n1 number of ways and event B has n2 number of ways, the total is just an addition. So this may sound rather abstract. Okay, let us just look at the example here. If let's say you can travel from your home to TP, to Temasek Poly, by 2 different routes using MRT and 4 different routes by bus, how many ways are there? So let us draw it out. So this is U. This is TP. Okay. So assuming that there are 2 ways by MRT. Okay, so this is MRT method 1, MRT method 2. And then you can have 4 different ways by bus. Okay, bus 1, bus 2, bus 3, bus 4. So how many ways are there to get to Temasek Poly? Okay, so for example, you can take from your home all the way to, let's say, Bedok Reservoir Station and then you walk over. You can take to Tampines East Station and walk over. Okay. Or you can take bus number 69. You can take bus number 23. You can take bus number 8. You can take bus 504, I think. So how many ways are there to get to TP? Effectively, you add up the number of ways for MRT plus the number of ways for bus. You end up with 6 ways because it is 2 plus 4. So this is what addition principle means. Okay. So essentially, there are 6 ways to get to Temasek Poly. Okay. However, what the next principle is your multiplication principle. Now, multiplication principle is that there are 2 events. Again, 2 events, event A and event B. However, these 2 events can occur in succession. That means one after another. Okay. In the first addition, A or B only. There is no succession. Now, for multiplication principle, you can have method A, then method B. In this way, how many total ways are there? You just multiply up. So for example, if you can get to school by taking a bus, followed by MRT. So there are 2 routes, bus then MRT. How many ways of getting there? So you just multiply it up. So what does this mean here? Let us go back to here. Let me just clean it off. So again, this is U. Okay, black. And this is U. So we talk about bus then MRT. So here is the MRT station. Okay. Or rather, then this is TP. Let's say that wherever you live, you may live in maybe Punggol. Okay. You have 4 different ways of getting to your MRT station. Bus 1, bus 2, bus 3, bus 4. And from Punggol station, you have 2 different MRT routes to get to TP. So how many ways are there? You can just multiply. Here is 4 times 2, which gives you 8 different ways. You can even list out what are the 8 different ways. You can have, okay, way number 1 is bus 1, MRT 1. Way number 2 is bus 1, MRT 2. Way number 3 is bus 2, MRT 1. Way number 4 is bus 2, MRT 2. Way number 5 is bus 3, MRT 1. Way number 6 is bus 3, MRT 2. Way number 7 is bus 4, MRT 1. Way number 8 is bus 4, MRT 2. So that's why you have 8 different ways. All right. So hopefully this should understand these 2 different ways of calculation. And essentially that is all that we need to know how to calculate. The rest of it, example 3, I leave it to you to go and read it up for yourself. I will not go through because it is not that critical. At the very least, you need to know how to calculate. If I give you whether 2 different ways or so. So let us go for another slight example. Let's say again, this is you. Okay. At home, but you have 2 options. For example, you can go to let's say MRT. This we have let's say Bedok. Okay. Or rather, let me just okay, let me just use a slightly different example. So assuming that from your bus you can go to Bedok interchange. Okay, you have 2 bus routes, buses from your place to Bedok interchange. Okay, and here is Tampines interchange. Okay, assuming that from your house you have 3 buses that can go to Tampines interchange, and here is TP. From Bedok interchange, you have 2 buses to go to TP. From Tampines interchange, let's say you have 4 buses to go to TP. So how many different ways are there? How many different ways you can get to TP? Let us just take the first one. Let me just block it up. This set first. Okay, we call it as via Bedok. Okay, so in the method via Bedok, how many ways? We know that it's multiplicative. We have 2 times 2. 2 ways to get to Bedok interchange, and then 2 ways to get to TP. So we end up with 4. Correct? After that, let me just use another color. We block this up, and we say that this is via Tampines. So via Tampines now, also we can multiply 3 ways from your house to get to Tampines interchange, multiply by 4 ways from Tampines interchange to get to TP. You end up with 12. In total, how many ways? Because these two, but from Bedok interchange and from Tampines interchange, they are disjoint. It's not one after the other. So then you add up. Let me just use a different color now. Oops, it's a different color now. Hello. Let me just. So now you have via Bedok plus via Tampines. So then that gives you 4 plus 12. You have a total of 16 different ways. You can actually kind of see that the way we calculate this is by multiplication principle. The way we calculate this is by addition principle. Okay, so this is what these 2 principles really means to you. So far, so good? Okay, then let us go to a third aspect. Now we come to this concept known as combinations and permutations. Now, to understand combination and permutation, there is only one thing. I'll rather start with an example here. Okay. A and B, A, B, B, A. A, B, B, A, I will say that it is one combination, 2 permutation. Okay. Because why? Combination, the order does not matter. Okay, you can, whether you take a bunch of bananas first or you take a bunch of apples first, it doesn't matter. The end basket is still one bunch of banana, one apple, or one bag of apples. Okay, permutation, the order matters. Whether you do A first or B first, it matters. So let's say when you're cooking, is permutation more important or combination? Let's say when you're frying something, obviously permutation is more important. You cannot, if let's say you have, can you put oil first, then fish, or fish first, then oil? Obviously, it matters, right? If you oil fish, you will cook well. You can fry your fish pretty well. Here, you have the fish that sticks to the wok. the end result is different. Okay. So, however, in shopping, it doesn't matter. In shopping, whether you take apples first, then bananas, or bananas first, then apples, the end shopping bag is the same. Okay. So how do we calculate it? The number one concept that you have to remember is there's this mathematical form known as factorial. Okay. Factorial, the notation is exclamation. So factorial of n. N is a number. We just write it as n exclamation. So what is factorial? So for example, I say factorial of 5. It simply means 5 times 4 times 3 times 2 times 1. Factorial of 10 simply means 10 times 9 times 8 and so on all the way to 1. What is the number? This is what factorial really means. Okay. So in your calculator, there's actually this factorial function, but because the number increases tremendously, you can end up, there's a limit to how much you can calculate. Okay. Now, so let's go through examples, given that permutation, the order is important. Okay. So how many ways can we arrange 3 letters A, B, C? Okay. So there are actually 6 ways. So these are the 6 ways as listed. Why are there 6 ways? Okay. So let's say we want to, how many ways are there to organize A, B, C? We have 3 boxes, correct? No matter which one, we take A. So why is that? Why is it 3 times 2 times 1 possibility, which is here will be 6. Okay. Because there are 3 boxes, there are 3 alphabets. So how many ways are there to put 1 alphabet into here? 1, 2, 3. So it can be A, B, or C. It doesn't matter. So there are 3 ways to put it here. Okay. No, once you use up either one, it doesn't matter which one you use up. It can be A, can be B, or can be C. You end up with, let's say here we take A. Okay, you end up with just B or C to put in the second box. So there's only 2. Does it mean that you put B? There's only 1 left to put here. So based on your multiplication principle that we have just now, okay, you have 3 ways for box 1. After that, you have 2 ways for box 2, and then 1 way for box 3. You end up with 3 times 2 times 1. That gives you your 6 different ways. Okay, this is where multiplication principle comes in here. All right. Okay, it is almost, yeah, so this is how it works so far. Okay, now, so let's go down. In permutation, we want to look at, let's say you have multiple items. Okay, how are they able to collect different things? So let's say, if I give you, oops, I just closed the wrong thing. Let me give you a slightly different example now. For example, if I have A, B, C, D, E, I have 5 objects. My question is, how many ways that I can select 3 objects from these 5 objects so that the order okay, go on. 5 permutate 3. So now this is actually the equation to calculate. It is n factorial divided by n minus r factorial. So in this case, will be 5 factorial divided by 5 minus 3 factorial. Okay, so it's actually 5 factorial divided by 5 minus 3 is 2 factorial, which is then 5 times 3, 5 times 4 times 3 times 2 times 1 divided by 2 times 1. So you cancel off, which is just 5 times 4 times 3. So 5 times 4 is 20. 20 times 3 will be 60. Okay, so far so good. All right. Now, we can also calculate, remember now we have another aspect which is called your permutation or combination. So because order matters, we use permutation. Okay. What happens if, how many ways can I select 3 objects from 5 objects so that the order doesn't matter? Okay. If order does not matter, then I use combination. Remember combination, A, B, B, A is the same. So will be 5 combinate 3. Okay. Then the equation will be this. In fact, you can press this on your calculator. Okay. So you just have a R, addition R here, R factorial here. Okay. So which means that this is 5 factorial, 3 factorial, and 5 minus 3 factorial. Okay. So let's say this is 5 factorial, 3 factorial, and 2 factorial. Okay, so you can actually press it in your calculator. In fact, there's a function on calculator just to do this. Okay. So that is all about permutation and combination that you need to know how to calculate. Okay. 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 So here, how many ways are there to arrange 2 letters out of 3 letters A, B, C? So there are 6 ways. The way to calculate it is by using permutation. You have 3 in total, and you choose 2. So in 3 factorial divided by 1 factorial is 6. Okay. How many ways to select 3 out of 2 letters? 2 letters out of 3 letters. Okay. Any 2. Okay. So here there's any 2 ways which you can use using combination. So there are in total of 3 ways. Okay. You can, example 7 and the rest, I leave it to you to go and read it up because they are not really that important. All I need you to know is how to calculate combination and permutation if the question comes up something like this. How many ways are there to arrange? Arrange means that the order matters. Select means that the order does not matter. Okay. In short, I want you to be able to tell me what is the difference between combination and permutation. That is all. Okay, we'll see you for next round. That's all. Okay, so now we are in the part 2 where we look at more on the probability itself. So before we go into probability, we have a few important aspects, terminology to actually explain. Number one is this thing known as sample space. Sample space usually is denoted by S. It's essentially all the possible outcomes. Okay, so for example, if you throw a dice, okay, what are all the possible outcomes from a single die? Okay, so the possible outcome for a single die is 1, 2, 3, 4, 5, 6. So these are all the possible outcomes. So which means that we can call this as sample space S. Okay, so that's sample space. Now, a subset of sample space is actually called an event. So in this context, we can say that 2 is an event. Okay, the getting a number 2 is an event, or getting a number 2, 3, or 4 can also be an event. Okay, or getting a odd number 1, 3, 5 can also be an event. So event need not be just one possibility. One of the 6 can be multiples. Okay, then we look at the last part, which is this concept known as probability. The probability of an event happening. That means what is the chance of an event happening? Okay, the chance of an event happening is given by this equation. Let's say the chance, the probability of A happening is actually given by this equation. The number of times A can happen versus the total number of chance. Okay, so using this concept, let's go back to here. What is the probability of getting a 2 when you have a throw of dice? The probability of getting a 2 is there's only one 2 here, so it's 1s out of 6. Okay, so it's 1/6. However, the probability of getting an even number, which is equates to the probability of getting 2, 4, or 6. There are 3 of them. So 2, 4, or 6 with 3 divided by the total sample size or sample space, which is 6. Then you have half or 50%. Now you know that if you throw a dice, half of the time you are going to get an odd number, half of the time you are going to get an even number. Okay. What I need to explain to you is this 50% or half of the time, we are talking about many tries. Okay, it doesn't mean that the first time, let's say it doesn't mean this. Okay, it doesn't mean that when you throw a dice, okay, the first outcome you get a 2. Okay, the second outcome you must get an odd number. Okay, no, this is not correct. It just means that if you throw the dice, let's say 1,000 times, okay, you will end up approximately 500 times, approximately only 500 times, getting an even number, and 500 times getting an odd number. It may not be exactly 500 as well. Okay, if you throw 10,000 times, then you end up with 5,000, 5,000, approximately. Okay, so this is what it means. It doesn't tell you what is the next outcome, but what is the likelihood of the next outcome. Okay. So having said that, we already touched on with your example 13. If you throw a die, the sample space is 1. The sample space is 1, 2, 3, 4, 5, 6. Okay, or you can split it into even and odd numbers. So the possibility or the probability of getting an even number is 3 out of 6. Similarly, the probability of getting an odd number is 3 out of 6, which is also the probability of getting an even number. Okay, so this is what it means. Probability of getting even number is also the same as probability of getting an odd number. Okay, with this concept, we can look at some of the features or properties of probability. Now, for any given event, the probability is bounded between 0 and 1. Okay, 0 means no percent. Okay, so if the event, what am I doing here? Okay, so if, okay, in event that the probability is 1, that means certainty. Certain, it will happen. Okay, or in this case, it's 100% that it will happen. The probability of getting if the probability is 0 means that 100% it is not going to happen. It's impossible. Impossibility. So the probability, the larger the probability, means that the more likely the event will happen. Okay. So we actually do a different thing. Okay. For example, let's go back to our dice to look at this thing called complement. Okay. We have our dice here. Let me just write it. 1, 2, 3, 4, 5, 6. Okay. Now, what is the probability of not getting 2 or 3? Okay. The probability of not getting 2 or 3 is actually the total probability minus the probability of getting 2 or 3. Okay. This is what it means. Okay. So 2 or 3 now becomes a complement. Okay. The reason is, if you take the probability of not getting 2 or 3 plus the probability of getting 2 or 3 will be equals to 1. Because why? The probability of not getting a 2 or 3 means what? Getting a 1, 4, 5, 6. Plus the probability of getting a 2 or 3 equals to 1. Because this is 4 out of 6 chance plus 2 out of 6 chance, which gives you 6 out of 6 equals to 1. Okay, this is what complement means. Now, very often, we can use a Venn diagram to represent. Okay, a Venn diagram simply means that the sample space A prime, which is the complement of A, is out of sample size A. So back to here, we can say that 2 or 3, right? Let me just shade it. So the probability, this is, okay, let me just shade it up. So this is equivalent to PA. Okay, then the rest of it, which is this, is equivalent to PA prime. Okay, make sense? Because we're coming back to this concept again. Okay. So that is the main part of probability. We have to look at what is the total number of, what is the sample space. Okay. Now, so this is mathematically what we have. Okay, the probability of A happening versus the divide by the total occurrence, and then the probability of A prime, which is not A happening, divided by the total occurrence, will give you 1. So we can actually represent it using a Venn diagram or tree diagram. This is up to you. So we look at coin. Okay, a regular coin, you have 2 coin toss. So every time you can get a head or tail. Okay, so what is the probability of getting 2 heads? Again, this is using your multiplication principle. So it's half times half, which is 1/4. Okay, the probability of getting a head then a tail, head then a tail, is also 1/4. The probability of getting a tail then a head is also 1/4. The probability of getting 2 tails is also 1/4. Okay. However, what if I do, so this is, remember, this head and tail, tail and head is 2 permutation, 1 combination. So what is the probability of getting 2 faces? Okay, will actually be this: 1/4 plus 1/4 equals to half of the time. 2 faces means that you can head tail or tail head. So you can extend this to 3 coin toss, 4 coin toss, unlimited number of coin toss. You can actually calculate all the probabilities out as well. Okay, and that will be quite interesting. Okay, so coin is very often used as a scenario because we can also do the same with dice, just that dice is much harder to deal with. You have 6 outcomes: 1, 2, 3, 4, 5, 6. So it's 1, 2, 3, 4, 5, 6. The second toss is 1, 2, 3, 4, 5, 6 again. Okay, so it's 1, 2, 3, 4, 5, 6. So what is the probability of getting a 1 and 1? It's 1/6 times 1/6. Okay, so the probability is 1/6 times 1/6, which is 1 out of 36. Okay, similarly, the probability of getting a 6/6 is also 1 out of 36. Okay, all right. Okay, so you can actually use this to look at different coin toss. Usually, if you can, I tend to prefer to use a tree diagram than a Venn diagram. There are Venn diagram solution, there are 4 spaces, out of which the probability is just 1 out of 4. Okay, during your secondary school days, you find that the tree diagram works much better. The probability diagram is a bit unusual for you as well. So stick with one that works for you. I prefer the tree diagram because that reminds me of how I do things back in primary school. So consider this scenario, probability of event happening. What is the probability that the 2 coins will turn up head? Okay, so out of the sample space, that's 4 possibility. So there's only one time the head will appear. So it's 1/4. The probability of only 1 head will turn up. So it can be 1 head or 1 tail, which means that it is half. Okay. So same thing for your dice as well. Okay, dice sometimes, okay, the only disadvantage of a tree diagram is you already have seen here. Okay, it's just too many to list. So another method is to look at it using a probability diagram. Okay, so let's say based on this question, okay, when 2 dice, fair dice is thrown. Fair means that there's unbiasedness. What is the probability that the dice show a odd score? Okay, let's just do the first one, odd score first. Okay, or then the opposite way, the sum is even. So how are you going to do that? You can do the tree diagram, which then takes a fair bit of paper space. The easiest way then is to do your table. So if 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. Then we fill up all the numbers. 1 and 1. If 2 dice is 1 and 1, we have 2 here. 1 and 2, we have 3. 1 and 3, we have 4, 5, 6, 7. 2 and 1, we have 2 and 1, we have 3. 2 and 1, we have 2 as well. 2 and 1, 2. Okay. So 2 and 2, we have 4. 2 and 3, we have 6. 2 and 3, 5. 2 and 1, we have 3. Okay. Let me just erase it. Okay, 5, 6, 7, 8. 3 and 1, we have 4. Okay, So 3 and 1 and 4, 5. This 6, this 7. Okay. So 4, 5, 6, 7, 8, 9, 5, 6, 7, 8, 9, 10, 6, 7, 8, 9, 10, 11, and 8, 9, 10, 11, 12. So these are all the probabilities. So what is the probability of getting a odd number? Is it odd number? Yeah, just see. Go back. Hello. Yeah, odd number. So what's the probability of getting an odd number? Now, simple. Just shape. Okay. Odd number, we have 1 here, 2 here, 3 here, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. Okay. So we have 18 out of total 36 because 6 times 6. So it is half or 50%. Those unshaded one will be the even, right? Also 18 and 36, also half. Okay, so this is how you can do it. Okay. So you can show all the possible outcomes. Okay, why do you have this? Okay, at least one dice shows an odd number. Okay, at least one dice shows an odd number. So I'm actually answering a slightly different question. So at least one dice shows an odd number. You have all the ones. Okay. So in that case, we have all the ones. Because all the one dice will show an odd number, and then you have this as well. Okay. So you end up with 27 out of 36. So it's 0.75. Okay. So I'm answering a slightly different question to here. Okay. So the probability of one dice getting an odd number. So probability of at least one dice being odd. Okay. What is the probability? Originally we have 18. Okay. The total is 36. So what is the others? Let me just use a slightly different pen. Okay. So dice number 1 will be odd number. So this as well. Okay. This column will also be odd number. Okay. Let's see. Yeah. So we have 3 and 5 also. So 3, because 3, the dice also give us an odd number. Okay. Then we have erase this because these are no longer. Okay. So let me just redo the whole thing all over again. Make life easier. So we have 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6. So the real one is the probability of at least one dice being odd. Okay. We already know that the total probability is 36. So what is one dice being odd? Okay. This 2, 3, 4, 5, 6. Okay. Then 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27. So this is where you get 27 out of 36, okay, which is 0.75. All right. Okay. So you can do for the other one as well. Now, example 17 is a bit more complicated. I'll leave this for you to do. So it's looking at vowels and so on. If you do not understand example 17, that's also fine. Okay, so this is what we have covered in your probability. Please understand this subsection well enough before we go to the next part called conditional probability. Okay, that's all for now. See you. Okay, so moving on, we are looking at the next concept, which is your mutual exclusivity and independent events. Okay, so what are mutual exclusive and independent events? So take a look at it here. When we want to combine events, there are two different things, union and intersection. Okay, now if you remember your sets theory in your secondary school, this is union. Okay, this is intersection. So which means that in probabilistic terms, the union of two events, let's say event A and B, it is the collection of outcomes that belong to A or B. So event A or event B can happen. It doesn't matter. Okay. So for example, let's say the probability of, let's say a probability that a person is a male, or probability a person is a female, or the probability of a person being a male is 100%. Okay, that's not considering hermaphrodites and so on. Okay, because these two is either you are male or you are female, but the union of it is inclusive. The intersection is when the outcome belongs to both. So this also means that you cannot be a male and a female at the same time. Okay, this it will be 0. So if we consider two events using a Venn diagram, the union will be the total of A, the probability of A, plus the probability of B, minus the probability of this intersection, because otherwise there will be double of this intersection, okay, because it's overlap. So how do we calculate it? Let's come to an example. Let's say we go back to our dice again. Okay. So event A is the probability of getting an even number. Okay, A is the probability of even number. B is the probability of divisible by 3. B means that divisible by 3. So what is the probability of A, B, and A union B? A intersects B. Okay, so let's say that this is union, this is intersect. Okay, so what is probability of A and probability of B? This you should know already. So probability of A, let me just find a space to write. Since the total sample space is 1, 2, 3, 4, 5, 6, the probability of getting a A, which is even number. So how many even numbers are there? 2, 4, and 6. So there's 3 out of 6 chance. We have 0.5, half our time. Correct? Now, for B, it is the probability where the number is divisible by 3. So which of these numbers are divisible by 3? It's only 3 and 6. So we have 2 out of 6 chance. The rest are not divisible by 3. So it will be 1/3 or 0.33. All right. So then, what is the probability of A union B? All right. So for A union B, what we have is 1/6 of a time. Oh, no, we add up together. So we just add up these two numbers. Half plus 1/3 minus of what is overlapping between the two. So the item 6 is divisible, is an even number and is divisible by 3. So we minus 1/6 of a time. Okay. And that is where we get this 2/3. All right. So A intersects B. That means find the probability of a number that is both divisible by 3 and even number. So which one will fall under this case? There's only 6, correct? Only 6. So it's 1/6 of a time. And this is where we get the 1/6 from. Okay, so this is how we can use your union and intersect to find probabilities if you need to. How about events that are mutually exclusive? We talked about it just now, that you cannot be a male and a female. If the probability of the intersect is 0, okay, that means that it is mutually exclusive. These two events cannot happen at the same time. Okay, this is by definition. So for example, when a dice is thrown, is it possible to get an even number and yet the sum is 11? The sum is even number is 11. We can't, because 11 is not an even number. Therefore, the probability of getting a sum, let's say for 2 dice that's even, and the probability of getting the sum that's 11 is 0. Okay, there's no such thing. It can happen at the same time. Okay, so this is where we have the probability of getting a even number is 3 out of 36 chance, because remember we come from last week, we have 6 out of 6. Okay, the probability of getting 11, okay, is 2 out of 36 chance, because how do you get 11? You can throw 2 dice that gives you 5 and 6, or 6 and 5. So there are 2 chance out of 36 chance. So it's 2 out of 36 or 1 out of 18. Okay. Now in union, so the chances of getting, what does this mean is the probability of sum being even or sum is 11. Okay, so you just add up the two probabilities together. Okay, when you add up, you don't have to minus the intersect because there is no intersect. You add them this way. This is A, this is B. Okay, sum is even, sum is 11 in this whole space. A and B doesn't intersect. That's why it's actually 1/2 plus 1/18 minus 0, because there's no intersect. So it's 5/9. Okay, so far so good. Now, the next thing we are looking at is independent events. Okay, we always say that when 2 events are considered independent, provided when one of the outcome doesn't affect the other. For example, remember you throw your coin. Your coin, you have head or tail. After you throw the coin the first time, does the outcome, either being head or tail, affect the second outcome? If it doesn't, then this is what we call as independent event. The second outcome is not affected by the first outcome. Okay, so when we come to independent event, we can just multiply the probability to give a intersect. Okay, so this is why we can take half, multiply by half to give us the probability of a head. Head is actually 1/4. Okay, because these two events, event 1 and event 2, they are not affecting each other. Okay, this is if the events are affecting each other, then they are not independent. So independent events and mutually exclusive events are two different things. Please do not get confused. The concept you have to know. Okay. So let's look at example 20. What is the probability of getting two heads if the coin is flipped twice? Okay. Does getting head on the first flip independent of the probability of getting the head on the second flip? No. So for here, just now we've answered it. Yes, they are independent. The independent of the outcome of the first coin toss doesn't dictate or doesn't give any chance of the second coin toss. So the probability of getting two head is 1/4, half times half, which is what we have here. Okay. And since we can just multiply them together, the first toss is independent of the second toss. Okay. So far, so good. Now, how do we know if something is independent or not? We have to check whether can we actually multiply them. So for that, we will not go through in detail. Example 21 actually gives you a solution to that, one of the examples that you can use. But we'll not go through that. At least what I need you to know is the concept. What are independent events? Okay. What are independent events? So this, in theory, you have to know what independent events, what are mutually exclusive events. Okay. And then finally, what is union and intersection? So if you know these four concepts, then you're okay for this. Okay. And in concept-wise, you don't have to show is it independent or not independent. Okay. All right, that's all for this topic 3.4. See you again. Okay. Next, we come to this concept of conditional probability, okay, which is not easy to calculate. Please listen more clearly. Conditional probability. So we want to know a few things. Okay. Given that there are two events, A and B. Okay. So what is the probability of event A happening given that event B has already happened? So that is conditional probability. So we read this as the probability of A given that B has taken place. Okay. So that's conditional probability. Now, it also means that the probability of B cannot be 0. So by equation, this is what happens. We will write the equation. Condition that event A happens given the event B happens is actually the union, the intersect, divide by event B happening, the number of ways that event A and event B. So this is actually the intersect. And this is where we realize that we need the intersect from the previous lesson. Okay? Intersection, divide by event B that can happen. Okay? Here also take note, important, the probability. Okay, I'll write this out here. Okay. Let me just take this. So B A is not equals to A B, which means that the probability of event B happening given that A has happened is not equals to the probability of A happening given that B has happened. Okay. Hope you can understand why. Okay, let me just show it to you why. Remember back to our equation. back to this equation here. Okay, let's come to it. So the probability of event A happening given that event B has happened, we write down as A, probability of A intersect B, divide by the probability of B happening. Correct? On the other hand, the probability of B happening given that A has happened will be, the numerator will be the same. A intersect B. Okay, let me go back. A intersects B. However, the denominator is different, the probability of A. Which is why these two are not equals, because the denominator are different. Okay, hopefully this is clear to you. So please do not mix it up. Okay, so let's say, look at this example. Assuming that the probability that is a rainy day in Singapore is 20%, 0.2. So John travels to school. So probability of rain equals 0.2. John travels to school via bus or taxi. So the probability of him traveling on taxi when it's a rainy day is 0.7, and on 0 is 10% of chance if it's a sunny day. So find the probability that John will take a taxi to school, and find the probability that John will take a bus given that it's raining. So find the probability of John will take a bus given that it is raining. If it's a sunny day, given that, what is the probability that it's a sunny day given that John takes a taxi to school? So it will be the reverse. So what is the sunny or non-rainy given that John takes a taxi to school? Okay, this is John taking a taxi to school. All right. So the solution is this. When John takes a taxi, what is the probability? We have John taking a taxi regardless of whether it's rainy or sunny. Okay, if you look at the diagram here, we can actually say, so rainy, here says that, okay, question says that Singapore rains 20% of the time. Okay, so it means that it is sunny 80% of the time or not raining. So 80, 20. Okay, so when it is raining, John takes a 70% of the time, John takes a cab. Okay, so here 70%, so this is given. So if it's, which means that the other 30% is taking a bus. Okay, so let me circle all the red that's given. If it is sunny, John takes the cab 10% of the time. So these three numbers are given. We just take one minus the others, and then we find the other set of numbers. Okay, so this 0.3, 0.9, 0.8 is actually calculated because it's 1 minus 0.2 and so on. So what is the probability that John takes a taxi? So John takes a taxi twice, okay, in two outcomes. One is when it's raining and takes a taxi, when it's sunny and taking a taxi. So you have the probability is 0.2 times 0.7 and 0.8 times 0.1. So collectively, this is what you have. Okay. So the probability of John taking a taxi is 0.22, 22% of chance. So far, so good. Okay, then we go to the next step. What is the probability that John takes a bus when it is raining? That means you already know that it's rain. So now you're waiting for John in the lecture room. What is the probability that John comes in and says that he takes a bus? Okay. So given the formula, it is bus and raining. So we look at bus and raining. Okay. So bus and raining is 0.2 times 0.3. So we get this, 0.2 times 0.3. The probability of it raining, 0.2. So we have 30% of the chance. Okay. The other hand, what is the probability that it's a sunny day given that John takes a taxi? Okay. So we take sunny and taxi. Sunny and taxi is 0.8 times 0.1. Correct? So the numerator is 0.8 times 0.1. And the probability of John taking a taxi. We already have that in our first part, which is 0.22. So you multiply up is about let me see, around 36% or so, because I just use my method calculation to divide out about 36 to 38%. So far so good. Okay, so we can technically use this to find out whether are these two events independent or not. Okay, by using this thing known as a calculation, by using a multiplicative rule for here. Now, very often we realize that it's not easy to find the union that easily, but we can use it to find the independent cases. What happens if you cannot find this? We can use these two formulas to help us. Because if you go back, okay, now, since these two numerator are identical, correct? So we can multiply it, probability of A given B, cross multiplied by the probability of B is actually equals to the probability of A intersect B for this part. And then for here, we just cross multiply. It's also the probability of A intersect B equals to the probability of B given A multiplied by the probability of A. We realize that these two are equal now. Okay, and that is what we are trying to show you in this case. So far, so good. Okay. Question 23, I leave it to you to work it out yourself. It is what happens when we want to find the intersection. Okay, so it gives you a scenario. So I leave it to you to work out. So, okay, so now we'll next talk about random variables. So variables are essentially anything that you try to measure. Okay, so variables itself. So for example, when we throw a dice, the outcome of a dice is actually a variable. So a variable comes from a random experiment. So essentially, variable are anything that, whatever that we can measure. Essentially, that's what it is that we can measure. Okay. However, variables can be discrete or continuous. Discrete variables are simply whole numbers. Okay. So discrete variables are actually whole numbers, countable numbers. For example, it can be the example here will be the sum of score when, let's say, 1 or 2 dice is thrown. So you can, let's say with one dice, it'll be 1, 2, 3, 4, 5, 6. When you throw a dice, it cannot be 1.5, cannot be 1.25. So they are called discrete. Or the number of passengers, example is the number of passengers arriving at the bus stop. It is a whole number. You cannot have 1.5 passenger. You cannot have 10.2 passengers. On the other hand, we can end up having a situation whereby variables can be continuous. The possible values of continuous is uncountable. For example, let's say height, okay, or length. For example, length. Length, you can have, 1 meter, 1.1 meter. You can have 10.2 centimeters. You can have 10.22 centimeters, or 1.2 millimeters, and so on. So it is continuous. There's actually infinite number of decimal places that you can have. So common examples is amount of coffee. Amount of coffee here will be in milliliters or liters. You can have 500 ml of coffee or 250.5 ml of coffee or any number. Waiting time, why is it continuous? Because you can be having 30 minutes. you can have 32.1 minutes, okay, or 32.2 minutes. Then you can have 32.15 minutes and so on. So it is continuous. All right. Okay, so let's recap what we have learned so far. We have learned about number one, your combinations and permutations. Combination and permutation. We have also learned about probability. Okay, probability. And then finally, we learned about your variables. Now, variables we have just mentioned, it can be discrete, can be continuous. So now what we are going to do is, can we combine all these concepts? Can we combine your combination permutation, probability, and look at just discrete to answer questions such as what? Okay, answer questions such as, let's say you in a test, okay? In a test, there are maybe 10 MCQs, multiple choice questions, okay? Let's full stop. If you answer them randomly, answer all 10 questions randomly, what is the probability of getting, let's say a certain number, maybe what's the probability of getting 7 correct? So we want to look at this. Okay, first it is you answer randomly, and what's the probability of getting 7 correct? So this is the kind of question that we want to ask for this round. So we look at this concept known as binomial distribution. Now, binomial distribution comes from any experiment that has only 2 outcomes. If an experiment has only 2 outcomes, we call it a Bernoulli's trial. So 2 outcomes can be yes or no, correct or wrong. Okay, yes or no, correct or wrong. Remember, yes, correct or wrong, this is your MCQ questions, your true-false questions, all will be just correct or wrong. Okay. Now, we have an equation for looking at independent Bernoulli's trial, because independent Bernoulli's trial, for example, let's go back to this, our 10 MCQ question. When you answer one MCQ and you answer the other MCQ, it is independent. So as long as question number 1 don't affect question number 2 and so on, they are independent. So can we use that to calculate? We can. First and foremost, we have to look at what is the probability of success. So a probability of success can be a probability of getting correct answer. Okay, the probability of getting correct answer. So in this case, for a 4-choice MCQ, the probability of getting correct is, randomly will be 0.25. Okay. Then Q itself is actually the probability of correct complement, which is 1 minus P. So in this case, which is the probability of failure or the probability of not correct or incorrect. That means you get it wrong. Okay, will be 0.75. We can use this to actually help us calculate. Let's say you want to, out of 10 MCQ questions, what is the probability of getting 5 correct? What is the probability of getting 6 correct? You can use this equation. Okay, what does this equation say? N is the total number, C is the number of, you want to get it right, then you put it into this P and you substitute into this equation. However, there are a few conditions that needs to be fulfilled. Number 1 is the number of trials must be fixed. Okay, you have your test paper, that is 10 MCQ means 10 MCQ. Okay, the number of trials must be fixed. There's only two outcomes. Either you success or fail. You get it right or you get it wrong. Okay. The probability of P is constant, which means that every time you meet a new MCQ, the probability is constant. That means you have only 1/4 chance of getting it right. The trials are independent. It cannot be a non-independent trial. Okay. So how do we get to that? Let's look at question 24. Let's say the probability of a patient recover from SARS is 0.6, okay, which means that the probability recovered, equals 0.6, okay. So this is the P equals 0.6, which means that Q equals 0.4. 40% don't recover, okay, and 30 patients or 30 people have contracted it, so N equals to 30. What is the probability that at least 20 will survive? That means at least 20 recovered. So look back at this equation that we have just now. We substitute all the numbers, okay? So this is the equation that we're looking at. Let's substitute back all the numbers in. So here we have NCR of your P times your R times your Q of N minus R. Okay, so here 30, N is 30, R is 20. Okay, because we want to find exactly 20. P is 0.6, you have 60% chance of getting of recovery. R is 20. Q is 0.4 because 1 minus 0.6. Then 30 minus 20 will give you 10. So you put this in, you get about 1.15. 0.115, which means that you have about 11.5% chance of exactly 20 patients recovery out of 30. So far, so good? Okay. Okay. So can you actually answer our first question here? A 10-question MCQ. Let me erase this part. Answer our question here. 10 MCQ questions. If you answer randomly, what is the probability of getting exactly 7 correct? So N is 10. Okay, because it's MCQ, the probability, let's say a 4th question, is 0.25. The probability of getting wrong is 0.75. R, you want to get exactly 7 correct. So let us calculate this. Exactly 7. So will be equals to 10C7 multiplied by 0.25 of 7 multiplied by 0.75 of 3. Okay, so let's check back. Do we get this correct thing? Okay, so is N, these two will be minus of each other. Okay, so it will be 10 minus 7. So that's what we get here. Okay. Now, so let us use a calculator and find out the answer. So let me take my calculator out. 10 C7 is 120. Okay, multiply by 0.25 to the power of 7, multiply by 0.75 to the power of 3. Okay, multiply by 0.25 to the power of 7, multiply by 0.75 to the power of 3. Okay. So you end up with 0.003. Do you get that? Yep. So you have actually only 1 to 0.3% chance of getting 7 right. Okay, so that's a very small answer. Okay, so that is all we have for your binomial distribution. We will talk about your normal distribution next. So we'll see you again. Bye-bye.